Hello guys, good morning. All of you, please type in your name. Okay. Good morning. Did you finish your assignment that I have sent you on the group? Did you finish the assignment? Any doubt? Should I discuss that? Okay. Okay, fine. So what we do in the last half an hour, because I am accessing now this YouTube thing, so I cannot go to the WhatsApp group and check the questions. So what we do in the last half an hour, you can send me your doubt, your question number on the group. I will discuss them. Okay, there only. Fine. Yeah. So now you let me know. Last class we have discussed hyperconjugation, right? Have we discussed aromaticity? Few examples of aromatic compounds. Have we discussed that? Aromaticity we have discussed or not? Okay. So we have finished aromaticity, and we have also discussed few means how many, Vaishnavi? Okay. Let me know. Let me know, guys, quickly. Okay, aniline we have done. Correct. So just one example. You tell me this one. I think we have done this, but just to make it sure, I'm just giving you one example. Is it aromatic or what? Or even this one? These two molecules, A and B. Aromatic behavior, you tell me? A and B. Quickly. Okay. Yes, correct. So we have done it already, right? Right. Okay, so we'll move on. Okay, guys, so last class we have discussed hyperconjugation, and we have also seen that hyperconjugation is possible. Okay, I am moving forward now. Just 5 minutes quick revision of this and then we'll move on. Okay. Hyperconjugation is possible in unsaturated compound like alkene, alkyne. It is also possible in carbocation and in free radical. In these three cases only hyperconjugation possible. Correct? Now, if we talk about the stability of alkene, this we have also discussed, right? And the condition for hyperconjugation is what? We must have sp3 hybridized alpha hydrogen, right? And the stability of alkene is directly proportional to number of hyperconjugative structure, which is also, we can say, the number of alpha hydrogen, which is sp3 hybridized, because this is the condition we have. Okay, more number of alpha hydrogen, more will be the hyperconjugative structure and more will be the stability, right? Next thing is what? The stability of alkene. And the stability of alkene in a given molecule, there are possibilities that resonance is also possible, I effect is also possible, and hyperconjugation is also possible in a given compound, right? So if there are different electronic effects possible in the molecule, then the stability order will define according to resonance first, then hyperconjugation, and then I effect. Means the order we have to follow in this way, right? If next thing you have to keep in mind, if the number of alpha hydrogen is different in all compounds, then stability, we can say, is directly proportional to the number of alpha hydrogen. We are considering only hyperconjugation here, if hyperconjugation is only possible into this, right? So depending on this, if I ask you one question here, which alkene is most stable here? Tell me. This is A, B, C, D, and then CH2 double bond CH2. Which one is most stable in all these? Arrange this in, yeah, and yeah, A, B, C, D. Why is it so? Because you see in all the molecule, here the number of alpha hydrogen will be 12. Number of alpha hydrogen is 9 here. Number of alpha hydrogen is 6. Number of alpha hydrogen is 3. And here we have no alpha hydrogen, right? The more number of alpha hydrogen, more will be the hyperconjugative structure and the stability will be more. So A is maximum, then B, then C, then D, and then E. And that is why you must have heard this, or you must know this, that more substituted alkene is more stable. Have you heard this? The stability of alkene, what we say? More substituted alkene is more stable. Yes? Reason behind this is what? Because more substitution, more will be the alpha hydrogen, right? You see, this alkene is the most substituted among the all, right? That's why it is more stable, right? The reason is hyperconjugation only. One more question we'll see. Tell me the stability of these two. See, these are the questions only we are discussing in the form of concept. We are discussing question only. This one and which one is more stable? A, B. Solve this question and we'll discuss. Nidhish, are you there? Nidhish? Okay. The first one, how many alpha hydrogen we have here? 2, 4, 6, 8. We have 8 alpha hydrogen. And here we have 3 and 1, 4 alpha hydrogen. So A is more stable than B. Right? Number of alpha hydrogen here will be 3, 5 and 7. Number of alpha hydrogen here is 3. So 7, since this one is more stable. Number of alpha hydrogen in this. How many alpha hydrogen we have here and here? Tell me. First compound, how many alpha hydrogen? Yeah, here we have 6. sp3 hybridized alpha hydrogen, right? So it is 6 and here it will be 2, right? So this one is more stable. In these two, which one is more stable? fifth one, which is more stable? Question number 5. See, in this what happens? This compound is aromatic and this compound is anti-aromatic. And that's why this is more stable. If you talk about this sixth one, which is more stable? See, the point I'm trying to make here, it is what? The given molecule, you never know that what all effects are possible. You have to analyze the compounds then. Like in all these compounds from 1 to 4, you see from 1 to 4, there is hyperconjugation possible. There's no resonance. But when resonance comes into the picture, then that will be the more stabilizing factor, right? So in the fifth example, you see the first compound is aromatic and the second compound is anti-aromatic. We do not have hyperconjugation here, but since the first one is aromatic, it is more stable. Correct? What about the sixth one? Which one is more stable? A is more stable. Why? Vaishnavi? Reason? Tell me. What is the reason for that? Correct, correct. So here we have resonance, right? So here we have resonance possible. Do we have hyperconjugation possible? Yes, we have hyperconjugation also possible here because of alpha hydrogen present, right? Here we have only hyperconjugation possible. So since resonance is there, so this is the more stabilizing factor here. First one is more stable than the second one. Okay, just a second. Hello. Yeah. Tell me, tell me. I have put it there in the center only. It's there in the classroom. You can check. Correct. Yeah. Okay, guys. Sorry. Got an urgent call actually, right? So here we have resonance, hyperconjugation. This one is more stable. Again, you see this pi bond here it is in conjugation, right? So hence this is more stable than the second one. So here also we have resonance possible and hyperconjugation also there, right? But here we do not have resonance, but hyperconjugation is there because of alpha hydrogen. So resonance is the more stabilizing factor we have here, right? So from all these examples, what Point I'm trying to make is what? You have to find out the stability of alkene. Because once you have what, because if the question is related with heat of hydrogenation or combustion, you have to deal with the stability of alkene. That's why I have given you all these examples. Okay. Now the next thing we are going to start here is heat of hydrogenation. Okay. So we'll start here, heat of hydrogenation. Suppose we'll write delta H hydrogenation like this. Okay. Now, what is heat of hydrogenation? It is the amount of heat released. It is the amount of heat. I'll write down in short. You also write down it quickly. Amount of heat released when 1 mole of alkene, 1 mole of alkene goes under hydrogenation. Right? Okay. For example, you see here, I'll go to the next page. I hope all of you have copied it down. Okay, for example, you see, if you have this molecule, suppose two molecules I am taking here. One is this, that is butene, and other one is this, which is butene. This is suppose molecule A, and this is molecule B, right? And when hydrogenation takes place, it forms butane. This also under hydrogenation gives butane. Okay, since in both the reaction we are getting butane here, so the energy of product will be same, right? And in these two, can you tell me which one is more stable, A or B? Which one is more stable, A or B? B is more stable. And why is that so? Why is that so? What is the reason behind that? More alpha hydrogen, correct. So this alkene is more substituted, and number of alpha hydrogen here it is 6, and here the number of alpha hydrogen is 2, right? So this one is more stable, right? So if I draw the energy profile of this reaction, right? Energy profile. So suppose, okay, this is the energy axis we have, right? And if I write down these two molecule A and B, if I try to put the energy profile of A and B, which one should be A, which one should be B? This should be A because B is more stable and less energy, right? It is more stable, hence it has less energy, and A is less stable, so we'll have more energy, right? So A will be here, B will be here, right? But the product here we have, that is suppose P, the energy of that product will be same because in both the reaction we are getting butane only, correct? So now here you see, if I draw the energy profile for B, it would be like this, and for A also it would be like this, right? Now the energy difference here you see, it will be for B, it will be this distance, that is delta HB, right? And for A, you see the energy difference will be this, that is delta HA. So if I talk about the magnitude of this energy which comes out in both the reaction, the magnitude of A will be is more than the magnitude of B, right? Plus, I'll write down here delta HA because it is an energy releases in this reaction delta HB. So magnitude of delta HA is more than to that of delta HB, and which is nothing but this energy is nothing but heat of hydrogenation. Heat of hydrogenation. So heat of hydrogenation of B is less, which is what? Which is more stable, right? This is more stable, less energy, right? So from this example, what we can conclude that more stable energy, sorry, more stable alkene gives, sorry, more stable alkene gives lesser heat of hydrogenation, right? So what we can write, the the stability of alkene is inversely proportional to the heat of hydrogenation. This is the first conclusion we can make here. Okay, did you understand this? Stability of alkene, you write down here. Stability of alkene. Is it clear? Okay. Now, one thing here you have to, the constraint we have, since you see A and B, both molecule has only one pi bond. So this relation is only true when the molecule has equal number of pi bonds. Okay, equal number of pi bonds. Then only it will be true. Otherwise, it is this we cannot say. But what happens if the molecule has different number of pi bonds? So for that, we'll write here for the molecule which has different number of pi bonds, then the heat of hydrogenation, delta H hydrogenation, is directly proportional to the number of pi bonds. Okay, this is the two things you have to keep in mind to compare the heat of hydrogenation. Okay. Now, one thing you see, what happens here? Why? See, these reactions are what? This process is exothermic energy releases, right? Exothermic process. Why it is exothermic? You try to understand. What happens in this reaction? You see, one pi and one sigma bond breaks, and we'll get what? Two sigma bond, because you see, when this pi bond, it means we have one hydrogen here attached with and one hydrogen here attached. The pi bond breaks and we'll get an hydrogen here. Here also what happens? We'll have an hydrogen here and we'll have an hydrogen here. This hydrogen is nothing but this hydrogen and this hydrogen. So what we can say, you see, one pi and one sigma bond breaks and we'll get two sigma. One pi, one sigma, we'll get two sigma, right? So pi bond, we know it is stronger than the sigma bond. So on the cost of one pi bond, we are getting one sigma bond, which has lesser energy, right? The difference in energy of this pi bond and one sigma bond will come out, and that's why it is an exothermic process, right? So if you have more number of pi bonds, right? More sigma bond will form, and more number of pi bonds will convert into sigma bond, and that is why more energy releases in that process. Correct? Now, these two things you have to memorize. Okay, that stability of alkene when we have equal number of pi bonds inversely proportional to heat of hydrogenation. When the number of pi bonds are different, then heat of hydrogenation will be directly proportional to the number of pi bonds present. Is it clear? Can you solve some questions now on this? Okay. One last thing I'll tell you here. When I say stability of alkene, so to decide the stability of alkene, right? We'll use all those factors that we have discussed just now in those examples, resonance, hyperconjugation, and all. Everything we'll see, right? Okay. So you see, we'll are going to discuss few questions here. You tell me the order of heat of hydrogenation, right? The question is the order of delta H hydrogenation. The first question here is A and B. A and B. Done. Solve all those questions, all the four questions. Then we'll start discussing it. Solve this, I'll get some water. Done. Okay, I'll do this. Okay. The molecule which has different number of pi bonds, right? So more number of pi bonds, more will be the heat of hydrogenation. So order of delta H hydrogenation will be this, right? These two molecules has equal number of pi bonds, right? But this alkene is more stable because of resonance, and here we have hyperconjugation, right? The alkene which is more stable is this, and we know that stability is inversely proportional to the heat of hydrogenation, hence the order will be this. Okay, right? Here you see that this alkene is stable because of resonance. Here only we have hyperconjugation. So which one is more stable? This one. Hence the heat of hydrogenation order will be this. Right? Now in this molecule, you see we have different number of pi bonds. Right? So according to the logic, you see the order should be what? If it is A, B, and C. Right? We know more number of pi bonds, more will be the stability, more will be the heat of hydrogenation. So order of heat of hydrogenation should be C, B, and then A. But this order is not found to be correct. This is not wrong. This is actually, this is wrong. This is actually an exception here. Why it is an exception, you see. This compound is benzene, which is highly stable because of aromaticity. Right? So one factor is reducing the heat of hydrogenation since it is highly stable. Right? The another factor, which is number of pi bonds, is increasing the heat of hydrogenation. Right? So both factors are contradictory to each other, and we know in chemistry when two factors are opposing each other, then the result becomes experimental in that case. Okay, and in this case, the result is, or the heat of hydrogenation is found to be in this order. B has maximum, then we have C, and then we have A. This is the order of heat of hydrogenation for this molecule. This particular example you must remember. You got it? Exceptions you must keep in mind. Okay. Okay. The next thing here we have to discuss is heat of combustion. HOC. Heat of combustion. Now in this only we'll write down the similar way. The heat of combustion is again inversely proportional to the stability of alkene. Stability of alkene. And when I say alkene, the stability of alkene, for that the deciding factors are what? Will decide the stability of alkene due to hyperconjugation, due to resonance, and due to aromaticity. Any of this factor can be there in the given question. Okay, all these three factors you have to look after. Okay, this condition is true when the two molecules has equal number of carbon atoms. This is true for the molecule has for equal number of carbon atoms. Number of carbon atoms. But if the number of carbon atoms are different, for different carbon atoms, the heat of hydrogenation, sorry, heat of combustion, HOC, is directly proportional to the number of carbon atoms. Right? So these are the two factors again you have to keep in mind. Okay. Now in this we have third possibility also, and that is if the molecule has double bond but different number of carbon atoms. This is not the special case. It comes under this only. Molecule has double bond but different number of carbon atoms. Then we also decide the heat of combustion is directly proportional to the number of carbon atoms. This factor is again dominating. This is a three case possible. This case, the last one comes under this only, but I have given here. Aromaticity is dominating. Okay, I will discuss this also today. See, for any carbocation, if you have, right, then aromaticity always dominates resonance. Aromaticity always dominates resonance. There is one factor which dominates aromaticity also, and that is dancing resonance. Okay, otherwise aromaticity is a dominating factor. Okay, so we'll discuss that also, but let me finish this thing quickly. Okay, you understood these 3 points you have to keep in mind for heat of combustion. Now we'll see some questions on this. Tell me the order of heat of combustion of these two molecules. First one, A B A B A B C D A B C D. Okay, what is the answer, guys? Uh, Correct. The first one you see, uh, the number of alpha hydrogen, the number of alpha hydrogen here in the first case will be what? Sorry. Number of alpha H is 9. Number of alpha H here, it will be what? We have 3 here and 2 here, right? So it will be 5. So this one is more stable and heat of combustion for this one is more. Inversely proportional to the stability, right? These two, what is the answer? What is the answer you have done for the second one? HA is more, right? You see, in this example is important, okay, and it's a good example also because when you look at this molecule, it has more number of alpha hydrogen compared to this one, right? But the point is, this molecule has more number of carbon atoms, right? Since this molecule has more number of carbon atoms, hence the heat of combustion of first will be more because it is directly proportional to the number of carbon atoms, right? So, however, hyperconjugation is there and more number of hyperconjugative structures are there, but since it has more number of carbon atoms, more will be the what we say heat of combustion. Now, in the third one, you see A, B, C, D, right? So it is all the molecules has different number of carbon atoms, and we know when the number of carbon atoms increases, heat of combustion increases. Got it? The fourth one, you see, fourth one, all the molecules has equal number of carbon atoms, right? But this one is least stable. Least stable. Why it is least stable? Because this has maximum angle strain. Maximum angle strain, right? So least stable, so most will be the hyperconjugate, sorry, heat of combustion. Order will be. Got it? So angle strain is also one of the factor, right? To determine the stability. One more example you see, the fifth one, heat of combustion order. A, B, C, D. Tell me the order. What is the answer for this one? DCBA, right? More number of carbon atoms. What we can say, more number of C. We have double bond, right? But the number of carbon atoms is also increased. There are different number of carbon atoms. The more number of carbon atoms, more will be the heat of combustion. So order will be this. Ritik, why it is DCBA, decreasing order? It's not stability, it's heat of combustion. Okay. Now, these are the few examples we have discussed. You will get questions like this only, especially heat of hydrogenation is important. So always consider the factor of stability of alkene. We can have hyperconjugation, we can have aromaticity, right? We can have resonance. These three factors can stabilize alkene. So whenever you have the questions, identify the stability order according to these three factors, whatever the possible factor we have, right? Aromaticity is most stable, then resonance, and then hyperconjugation. And inverse will be the heat of hydrogenation order, right? Now, like I said, hyperconjugation is possible in case of alkene, carbocation, and free radical, right? A few examples of carbocation also we see. So we have hyperconjugation in carbocation, right? So you see one example I'll write down CH2, CH2 positive charge here, and hydrogen will have here, right? So again we'll draw the hyperconjugative structure of this. This will come here, CH2H plus double bond CH2. This is the hyperconjugative structure. And similarly, we can draw two more hyperconjugative structure here because we have three alpha hydrogen present, right? Number of alpha hydrogen is three. So we can draw two more hyperconjugative structure, right? Here also, you see the stability of this carbocation, right? Which is affected by I effect also. But hyperconjugation also stabilizes this carbocation, right? So what we can say, the stability due to hyperconjugation, if I write, stability due to hyperconjugation is directly proportional to again the number of alpha hydrogen, right? Number of hyperconjugative structure here it is what? It is equals to the number of alpha hydrogen. Which condition should we consider for HOC stability? What is HOC? What is this HOC stability? Acha, heat of combustion, for heat of combustion stability or number of carbon atoms. Okay. See, heat of combustion is inversely proportional to stability, right? If you have equal number of carbon atoms, right? If you have equal number of carbon atoms, then we consider HOC is inversely proportional to stability, right? But if the molecule has different number of carbon atoms, suppose in the example, third example you have, if the molecule has different number of carbon atoms, then more number of carbon atoms, more will be the heat of combustion. Got it? If the molecule has different number of carbon atoms, then heat of combustion is directly proportional to the number of carbon atoms. Okay? But for equal number of carbon atoms, we'll check stability. Okay. Now you see, if one example I'll write down here, stability is directly proportional to number of alpha hydrogen because of hyperconjugation. You see this example, if you have this carbocation, H3C will have it. Okay, these three. Okay. So here you see, since we have sp3 hybridized carbon atom also present, alpha carbon atom also present, so here we have hyperconjugation possible and plus I effect also possible. The same thing we have here also, hyperconjugation and plus I. Hyperconjugation and plus I. Right. So which one is dominating factor here? Obviously hyperconjugation dominates over I effect. But the stability with both the factor you consider, you will get the same thing, right? Since hyperconjugation we are discussing, so number of alpha hydrogen is 9 over here, number of alpha hydrogen is 6 over here, number of alpha hydrogen is 3 over here. So order of stability will be this. Okay. Another example you see, right? What all effect possible? Again we have plus I hyperconjugation, plus I hyperconjugation, plus I hyperconjugation. Sorry, we have plus I hyperconjugation. But which one is dominating in all these? Hyperconjugation is dominating. And with hyperconjugation or plus I, whatever you consider, the stability will be maximum for this and then this, because this molecule has 7 alpha hydrogen, this molecule has 3 alpha hydrogen, and this molecule has 1 alpha hydrogen, right? But we compare the stability here for these two molecules, which one is more stable? We have CH2 plus CH plus CH3, CH3. Which one is more stable? Just a second, just a second. Wait a minute. We have CH2 and then CH2 plus this one. One more comparison I'll give you. Tell me the answer. Third one. Which one is more stable? Done. Fourth one, B is more stable than A. What about the third one? Third one, you tell me. A is more stable than B. Why A is more stable? Because this is resonance, right? And here we have hyperconjugation, right? So resonance is more stable. Fourth one, you see, we have alpha hydrogen 2 here. Here also we have alpha hydrogen 2. So we have equal hyperconjugative structure. But at the same time, here we have more plus I effect. Fourth one, we have more plus I effect because we have propyl group here, here we have ethyl group. And that is why the second one is more stable. So all these things are relative, you see. If you see the hyperconjugative structure, we'll have equal hyperconjugative structure, but I effect is a deciding factor here because we have more plus I here, lesser plus I here. So overall the stability of this carbocation will be more. Got it? Okay. Now, similarly, you see the same thing we have for free radical also. But the only difference is in this carbocation, we have complete transfer of electron. But in case of free radical, we'll have homolysis, right? One electron will go onto the one atom, right? So that's the thing. So I'm not going to discuss that free radical part again, right? It's the same thing, exactly same thing we have for free radical, right? Now, hyperconjugation, like resonance and I effect also, hyperconjugation also there are two types of hyperconjugation. There are two types. One is plus H and other one is minus H. Plus H are what? These are electron releasing effect, electron releasing group, like we have plus I and plus R. Similarly, minus H are electron withdrawing group. Which one? The second one. Wait, I'll see. In the second one, yeah, this is the stability order, right? This is the stability order. The heat of combustion will be reverse of this. Okay, so plus H minus H we have discussed already, so we are not going to discuss this again, right? But only thing minus H is possible in case of CCl3. Okay, that you must remember. CF3, CBr3, and CI3 minus H is not possible in these three cases. Okay, CCl3 and then CH. And you also know, since we have discussed that because of electron releasing group ERG, ortho or para position becomes what? Electron rich, right? And here the ortho and para position becomes electron deficient, and meta position is unaffected, right? And this is true in case of what? In case of resonance also, right? And the hyperconjugation plus H effect of CH3 is more than CD3 than CD3. This also I have discussed already, so I'm not going to discuss this again. Okay. Now, the application of this, you see, we are going to discuss now. Next slide, I'll write. You see, application of electronic effects. Application of electronic effects, right? In this section, what we are going to discuss, we are going to discuss the stability with all electronic effects, with respect to the all electronic effects. Okay. So first of all, you see, if you're talking about carbocation, this part is important because when you get the question, you have to apply all electronic effects possible. See, the stability of carbocation affects by these factors actually. Maximum is, this is the order I am giving you. Okay, in this order only will define the stability of carbocation. The first and the most dominating factor we have here is dancing resonance. I will discuss this. First, you write down dancing resonance. And the second factor we have when this positive charge or carbocation is a part of aromaticity. Right? Third factor we have plus M effect. Fourth we have plus H. Fifth we have plus I. Sixth we have hybridization. Hybridization. Seventh we have minus I, minus H, minus M, and the last factor is anti-aromaticity. Okay. Now the meaning of this order is what? The meaning of this order, you see, till from dancing resonance to this six, the first six thing are these are stabilizing factor. This will stabilize the carbocation. And these are destabilizing factor. Destabilizing factor. Okay. The meaning of this is what? Suppose in the given molecule, suppose four molecules are given, right? And in that four molecule, in one molecule we have aromaticity possible, in other one plus M, then plus H and plus I. So the molecule which shows aromaticity is most stable, then we'll have plus M, then plus H, and then plus I. This is the meaning of this. Understood? We'll discuss few questions into this, but first of all, since we haven't discussed this dancing resonance, we'll discuss that first. See, this dancing resonance is a special case. You have to actually memorize this. Only one case it is there. In case of, or what we say, this is a special case where sigma electrons are taking part in resonance. Sigma electrons are taking part in resonance. Remember one thing, in resonance only pi and lone pairs are involved. Pi electrons and lone pairs are involved, right? But in this case, sigma electrons are involved. For example, you see, if you have this carbocation, we have CH2 positive charge and we have a cyclopropyl group present. If I draw the resonating structure for this one, that will be this. Or this. We have positive charge here, positive charge here, right? Now in this what happens, this sigma electron, any one of these two sigma electrons comes over here, right, and form this molecule. If this comes over here, we'll get this molecule, correct? Why it happens? Because the cyclic cyclopropyl ring that you have, it has very high angle strain. Angle strain. And that is why this kind of resonating structure forms here. Okay. So this is the special dancing resonance is actually the special case of cyclopropyl ring. Okay. Whenever we have cyclopropyl ring, right? So for example, you see, you must have seen this question. The stability order of this molecule. This is given in OP Tandon also. They haven't given the reason here, but the question they have mentioned, the order of carbocation they have mentioned here. You must have seen this cyclopropyl, tricyclopropyl in benzene. So here in this case, what will be the order of stability? Which one is most stable? Which one is most stable? No, Vaishnavi, it's not the third one. Why? I'll tell you. When you have three cyclopropyl group, then this kind of structure you can draw even more here. Understood? This sigma electrons also takes part into resonance. This also and this also. So here you can draw more resonating structures, more similar resonating structure you can draw, right? And that is why the stability for this will be more than this and then this. The thing is, whatever you can do with one single ring, right, that you can do with the other ring also if it is present to the carbon. Got it? So similar kind of resonating structure, if suppose you replace this hydrogen atom with another cyclopropyl group here, then another more structure you can draw. Correct? Hence, this one is most stable, then this, and then this. Got it? Now the point is this order I have given you. Now suppose if I ask you that this is one molecule and along with these three, I have given you one other carbocation like this, and I ask you what is the stability order of A, B, C, and D. Now you see, since in these three molecule involves dancing resonance, right? And we know dancing resonance is preferred over aromaticity, right? That is why this is the order of, carbocation. This is most stable, then this, and then this, and then last we have carbocation. Is it understood? Similarly, if you have aromaticity and plus M, then aromatic carbocation is more stable, right? Plus M plus H plus M is more stable. Like this, you have to compare. So for that, you should know what is the condition of plus M we have, which all group shows plus M effect, where plus H is possible, where plus I is possible. You understood this? Now, on the basis of this only, now the question that we are going to discuss now, there we have application of all these factors, which affects the stability of carbocation. Correct? So now we are going to discuss the question here. Here we have discussed Okay. So first question I am giving you, tell me the stability of this carbocation. We have CH2 plus and here it is CN. OCH3. NR2. Cl and here we have CH2. Tell me these two first. The first one is BCDA. CBDA. Okay, tell me one thing here. First of all, see these type of questions. First of all, you should know what is the electronic effects we have here, because you see this part is common in all the compounds, right? The difference in stability will have because of the group attached here and the nature of these groups. Okay, so first of all, you tell me cyanide CN, what effects it shows? What effect it shows? Minus N, correct? So here we have, so first of all, you identify what effects are there. Minus M, here can I write it is plus M? NR2, what about NR2? Plus M, right? What about chlorine? Chlorine only minus I. However, the chlorine has lone pair on it, but it shows only minus I effect, right? Now, minus M and minus I are destabilizing factor because both are electron withdrawing group, right? So the positive charge density will increase and hence it is electron destabilizing, sorry, it is destabilizing factor. Plus M are electron releasing, it is stabilizing factor. So obviously B or C is more stable than A and D, correct? Yes, right. Right, Vaishnavi. Minus I is dominating for halogen. Correct. So B and C are more stable than A and D. A and D, if you compare, minus M dominates over minus I, and this will decrease stability. So obviously A will be the least stable, and then we'll have D. Correct? Now, depending on the nature of Nr2 and OCS3, which one has more plus M effect, the stability we can decide. Then Nr2 has more plus M effect, so stability will be B in the second, and then C will be the most stable. You understood this? Got it? Correct. Now, similarly, here you see CH3 shows plus I, NO2 minus M, CH3 plus I, right? So plus I is what? Plus I is carbocation stabilizing factor, right? Carbocation stabilizing factor. And minus M is destabilizing factor, right? Minus M is destabilizing factor. And along with plus I here, we can also have plus H possible. Hyperconjugation, right? Alpha carbon sp3 hybridized, right? And which one is dominating here? We know hyperconjugation dominates plus I. So here, if they ask you what is the dominating effect, answer will be hyperconjugation, right? Minus M, so this B will be the least stable, right? Plus I, then C, and the first will have A because of hyperconjugation. Yes, I have given the order also for this. And R2, this is, see, whenever you have two similar electronic effects, okay, plus M, minus M, whatever it is, then you should know that which one dominates on other. That you should know. This comparison you should know. I have given this order also. And R2 shows more plus M. Understood? Second one you understood? See, whenever you have alpha sp3 hybridized, alpha carbon present at ortho and para position will have hyperconjugation possible, right? So there will be the dominating factor is hyperconjugation. Now, another example you see. Tell me the stability order A, B, C, D. Tell me the order. Guys, done. What is the answer? D is maximum, then C, then A, and then B. Vaishnavi, are you done? See, it's simple only. You see here. What electronic effects we have here? Resonance, right? What we have here? Again, resonance. This one is aromatic. This one is also aromatic, right? Which one dominates? Aromaticity dominates resonance, right? So obviously these two are more stable than these two, right? Second thing, here we can have more resonating structure because we have two phenyl group, right? So obviously this B is more stable than A because of more RS here. Third will be what? Both are aromatic compounds, but here we'll have large conjugation, more number of RS possible here, more RS here, right? Hence, we'll have A, B, C, and D will be the most stable. Got it? This one you see? One more example. A, B, and then C. Done? What is the answer? Both of you are getting exactly reverse. Why are we making these mistakes? I don't know. Okay. One thing you tell me first of all, how to proceed this? What effect we have here in A? What effect possible? A, B, C. Okay. Here, what effect possible in A? You tell me. Resonance. Correct. Do we have hyperconjugation possible here? No, because the carbon atom is sp2 hybridized. No hyperconjugation. Here we have resonance again, right? So both will have resonance. If we compare the stability of this positive charge, since we have large conjugation here, obviously A is more stable than B, because in A we have more conjugation. Correct? Resonance is done. Here we have hyperconjugation possible, right? Plus H. sp3 hybridized alpha carbon atom. Hyperconjugation possible. And we know hyperconjugation resonance dominates hyperconjugative structure. Order will be AB. Is it clear? First of all, you see what effects are possible, and then you decide which effects dominates. According to that, you decide. Got it? Next question. Next topic we'll discuss. See, we have discussed for carbocation. Similarly, carbanion, stability of carbanion also follows this order. The first one is aromaticity. If the negative charge is a part of aromaticity. Second one is minus M. Resonance. Fourth one is minus H. Fifth one is minus I. And then sixth one is hybridization. These are stabilizing factor 1 to 6. Destabilizing factors are this. We have plus I, plus H, plus M, anti-aromaticity. Right? All these will stabilize because these are what? Electron withdrawing. Okay. Negative charge, electron withdrawing will minimize the charge over there. Right? Just one or two example we'll discuss here. NO2 attached here. CH2 negative anode. Stability order, first one, and one more we'll discuss is this. stability order. You see, I will discuss this. This here we have minus M, NO2 minus M. Here also we have minus M. So with minus M we cannot decide, right? Because minus M is only associated with pi bonds. It has nothing to do with the distance from this carbon ion. But along with minus M, it can also show what? Minus I effect. Here also it can also show minus I effect, right? So minus M is same at both ortho and para position. But if you have minus I present here, right, in this case, it is more effective here, right? Because it is closer to this carbon and a carbon ion, right? And that is why the stability of second one is more. You see, the dominating effect is minus M only. Okay, you understand this. Dominating effect is minus M only. But if you consider minus M, you cannot decide the you know stability of carbon ion because both group shows minus M, same group we have, right? And minus M is independent of distance. It has only associated with the conjugation of pi electrons, right? That is same for ortho and para position. So addition to this, what we can think of? We can think of I effect. But ortho position we have minus I and para also we have minus I. But since ortho is closer, then minus I dominates over there, and that will stabilize the carbon ion more. Got it? Understood this one? See, I am discussing only some miscellaneous examples, okay? Some good examples where you can make some mistake, where there are possibility of doing some mistakes. General thing, if you understand the concept and various effects, okay, you can do general questions easily. But these kind of questions, you may make some mistake into the exam. Okay, so this question you have understood. Question number one, tell me. Correct. Second one. And second one, you see, this is also a very good example here. See, because of this group present, methyl group present here, we have steric repulsion here. And here also we have steric repulsion. To minimize this steric repulsion, what happens? NO2 changes its plane, right? So one this group will go out into the plane, and this one will come probably out of the plane, like this. Okay, dark. This is a wedge line. Okay, it's dashed line. This will change its plane, and because of this change in plane, minus M is not possible. Minus M effect is not possible here, right? So, and here minus M effect is possible, so this will stabilize more. Order will be this. If ortho positions are occupied, then steric repulsion will come into the picture. Got it? Okay, some acidic order we'll discuss. Tell me the acidic order of this compound. COOH. Here we have CT3, COOH, CD3, COOH, CH3. Second one, COOH, CH3, COOH, CH3. These three questions. Yeah, I'll give you the break. Give you the break. Wait. Okay, these three questions you do, then we'll take a break. Okay, I'll discuss this. Wait. See, first of all, acidity, little bit of idea you have, right? The acidic strength, just give me 10 minutes, we'll give you the break. Acidic strength, but please concentrate. Acidic strength is directly proportional to the stability of its conjugate base, which is nothing but an anion, right? So acidic strength, in other way you can say, it is directly proportional to the stability of anion. So that we have already discussed in case of carbanion, but here we don't have carbanion here, but anion will have, right? So if you form the conjugate base of this, will get negative charge on this oxygen here and here. Now this stability will increase if you have electron withdrawing group present. Correct? Electron withdrawing group present. So what we can say, acidic strength is directly proportional to EWG and inversely proportional to ERG. Is it clear till here? Yes or no, guys? Tell me. Correct. Correct. So you see, now again the same thing. CT3 shows this effect. It shows plus H. Yes or no? It shows plus I also, but plus S is dominating. CD3 also shows plus H effect, and CS3 also shows plus H effect. Plus H effect are electron releasing effect, right? Electron releasing effect. So because of electron releasing nature, the acidic strength will decrease. Correct? Which one has maximum plus H effect? Which one shows maximum plus H effect? Tell me. CT3, CD3 or CH3? Maximum plus H. Tell me, order I have given you already. Order of plus H effect of CT3, CD3 and CH3. Which one shows maximum plus H effect? CH3, methyl group. It has maximum plus H nature. Means maximum electron releasing tendency. Hence the stability, or sorry, the acidity of this one will be least, order will be this. Is it clear? Guys, tell me. Quickly, we'll finish these two and then you can take a break. Okay. Now similarly here we have plus H effect at CS3. What effect will have here at this position? Yes, here we have only plus I because this is the meta position, and we know hyperconjugation and resonance does not affect meta position. So we'll have only plus I present here. Both electron releasing nature, plus H dominates over plus I, right? So order of stability will be this. Sorry, acidity will be this, right? Similarly, CH3, here we have plus H, NO2 minus M, and here we'll have plus M, OH, right? Minus M increases the stability, you see here, uh, directly proportional to EWG. So it is EWG. So this one is the most acidic, first one, plus M plus H, electron releasing. This will release more electron than this. This acidity will be third and this will be second. Is it clear? Clear, yes or no? Okay. So what you have to do, first of all, you have to assign the effects, electronic effects, plus H, plus M, minus M, R, whatever it is, right? And then you have to see which one is electron releasing, which one is electron withdrawing. According to that, you can decide. Okay, so I won't take much time here. We can take a break here. Have your lunch. We'll start at 1:15. Correct? Okay, take a break. Guys, you there? Can we start now? Hello, guys, are you there? Hello, can we start? Okay. Okay, so you see, we have discussed about this derivative of benzoic acid, correct? And if you see all the examples here, we haven't taken ortho substituted benzoic acid, right? So now you'll see what happens if you have ortho substituted benzoic acid we have. Okay, so there is a effect, we call it as ortho effect, right? The heading you write down ortho effect. What is ortho effect? You see, if you have an ion like this, we have C double bond O minus, and we have CH3 present here, right? So since both groups are bulky here, so what happens, because of the steric hindrance present here, this CO2 changes its plane, and the structure will be like this. The CH3 present as it is. The CO2 molecule changes its plane, and one of this atom is coming towards the observer, O minus, and other atom, oxygen atom, is going away from the observer, like this. Okay? Because of this change in plane, the CO2 minus, or I'll write down like this, CO2 minus ion is not in resonance with the ring, right? But within this molecule, you see, within this CO2 itself, there is resonance possible, right? So it is not involved in resonance, but CO2 minus can show resonance within itself, right? And this is and forms, I'll write down, and forms equal RS, equal RS, because this is in resonance. So we have equal RS present here. Now, because of this equal RS, the benzoate ion is more stable, and hence more acidic. Since this ion is more stable, hence the whole molecule is more acidic. So what we can say, ortho substituted benzoic acid is more acidic, than para or meta substituted. This is ortho effect, right? Since you see the resonance is hindered over here because CO2 minus ion changes its plane. So we also call it as steric inhibition of resonance, which is nothing but SIR. So SIR effect or ortho effect are the same thing. Steric inhibition of resonance or ortho effect are the same thing, right? So this you must remember, because of ortho effect, the ortho benzoic acid means ortho substituted is more acidic than para or meta benzoic acid. Got it? Wherever you see ortho substituted benzoic acid, it should be more acidic. Understood? No, it won't depend on the substituent. Whenever you have ortho substituted, it is more acidic. Simple thing. Because COOH group is itself a large group here. So it won't depend on the substituent. Correct? Am I audible now? Am I audible? Okay, you can hear me, but you cannot see the screen, right? It's blank. I don't some okay, there are some, it's a network issue through. Okay, I'll send you the link again. Okay, we'll send you the link again. Wait.